Citao will present their work entitled A Multi-View Graph Contrastive Learning Framework for Cross-Domain Sequential Recommendations. The floor is yours.
Okay. Hello, everyone. My name is Zitao Xu. I am a postgraduate student from Shenzhen University. In this presentation, I am going to introduce a multi-view graph contrastive learning framework for cross-domain sequential recommendation. To begin with, let's see about the problem definition. In cross-domain sequential recommendation, we aim to predict the next possible item for each user in the target domain, based on his or her behavior sequence in the target domain and source domain. In this paper, we focus on two limitations of existing CDSR methods. Firstly, most methods capture the user's preference independently of each domain, which may neglect the item transition partners across sequence from different domains. Moreover, the data sparity problems still exist since some items in the target and source domain are interacted with only a limited number of times. So, to address these issues, we propose a generic contrastive framework named NGCL. Specifically, we target the problem from the perspective of intra-domain item representation view and the inter-domain user preference view. Here is the framework of our proposed MGCL. From the intra-domain item representation view, we jointly learn the dimensional sequential information in the user sequence graph and the static complementary information in the cross-domain global graph. From the inter-domain user preference view, we capture the complementary information of the user's sequential preference from different domains. Next, we introduce the intra-domain item representation views in detail in the following three sections. In the user sequence graph embedding learning, we aim to generate the item embedding and capture the complete item transition. Taking the target domain as the example, a user's sequence in the target domain can be modeled as a directed graph. We donate it as an embedding of the target domain sequence. Inspired by srGNN, we employ gate GNN as the user sequence graph encoder. After encoding, the item embedding in the target domain sequence graph can be donated as H. Similarly, we can contrast a source domain sequence graph and obtain the source domain item embeddings. In global graph embedding learning, we aggregated all user sequences in a cross-domain global graph and imported a global graph encoder to capture the collaborative information. The cross-domain global graph is an undirectly bipartite graph, and each user noise is linked to the item noise that he or her had interacted with. In such graph construction, the item noise from different domains can be associated through the user noise. Inspired by light GCN, we aggregated the features of neighborhood noise and obtain new representation for each new noise. Then, we can obtain the corresponding item embedding according to the index. To jointly learn the complementary information from different graphs, we apply the contrasting mechanism to the corresponding item embedding in the user sequential graph and the cross-domain global graph. Taking the target domain as an example, we feed each target domain item representation into a multi-layer positron. Then, we choose the representation for a same user from different graphs as a pair of positive samples, and the item representation of different users as a pair of negative samples. We adopt info NC as a binarity cross input cross between samples as our learning objective. Next, we introduce the inter-domain user preference view in detail in the following two sessions. In the sequential preference learning, we aggregated the graph embedding and imported sequence encoder to capture the user preference in different domains. We concat the representation of a same item from different graphs, feed it into an NLP, and the final representation of the item can be calculated by a weight sum. Next, we adopt a sequence encoder to capture the user dynamical preference and sequential dependence amongst items. In this paper, we utilize the architecture of Sazera's model. Consider that some users' preference in different domains may be similar in a period of time. Therefore, we apply the contrasting mechanism to the target domain and the source domain sequential preference. Since the item characteristics of different domains may be not consistent, we imported a mapping unions to reconstruct the user sequential preference in the source domain. To enable a user's preference from different domains complement each other and render self-supersized signal, we treat the sequential preference of some user in different domains as a pair of positive samples, while the preference of the two domain users as a pair of negative samples. In the prediction layer, we import concatenation to aggregate the sequential preference from different domains. And the final trending loss of our MGCL can be calculated as follows. In the experiment sessions, we studied the following 5 research questions. We conduct experiments on the Amazon dataset and choose movie, CD, and book domains from the date. And we process the datasets according to the following 4 sets. This table shows the statistical detail of the processed datasets. We adopt the hit rate attempt and NDCG attempt to evaluate the recommendation performance. Our baseline includes 2 generative recommendation messages and 8 sequential recommendation messages and 3 cross-domain sequential recommendation messages. Here are some implementation details of our work. The main result is shown in this table. We can adjust that our proposed model outperforms all the baseline on all the 3 datasets. And the CDSR message outperformed most single domain sequential recommendation messages, which indicates that the introduction of cross-domain information is often beneficial. Here are some other adjustments. We conduct 2 experiments to verify the effectiveness of introducing cross-domain information to elevate the data spotted problem. We divide users into the graph based on their behavior sequence length in the target domain and based on the range in the source domain while fixing the target domain sequence length interval. We can adjust that the maximum improvement of our MGCL against Sazera's model occurs in the source sequence interval. That's because the traditional single domain message structures to capture the user's preference in a spotty day, while the knowledge transfer across domain are more effective in this situation. We also conduct an ablation study to evaluate the contribution of different components of our MGCL. We can see that all the best results are from the composition of all the modules, which confirm they are complementary. to explore the health of contrasting learning mechanisms for learning item representation. We project the item embedding of the trained model into 2 dimensions by SBD and visualize the results. We can see that our MGCLO effectively expands the embedding space, and both high and low frequency items can be uniformly distributed at most E. We also conduct experiments to explore the influence of the weight of contrasting learning tasks. We can observe that the best results are achieved in most cases when the barrier is 0.5. Here is the summary of our work. We propose a generic framework for cross-domain sequential recommendation, and we adopt the item representation contrastive learning to achieve the complementation of the sequential information and the collaborative information. Moreover, we employed preference contrastive learning to enable knowledge transfer from different domains. Here is the directions of our future work. Thank you for your listening.
Thank you, Zitao. Thanks a lot. Questions? Please, we have plenty of time for questions.
Okay, can I? Hello, Zitao. I'm a student from NTU, and your work, MGCLA, I think is very brilliant. For your presentation, it seems MGCLA combines different kinds of methods. So I'm curious about that. Which part is the key modular in MGCLA that contributes to its great performance? Or in other words, can you talk more about the ablation experiments in this paper sense?
Okay, that's a great question. Thanks for your asking. Actually, we have conducted a abundant study to evaluate the contribution of different components of our MGCL. So firstly, we can observe that simply attaching the graph encoder cannot achieve better results, which may result in the data sparity problem. Moreover, aggregating the user's preference from different domains significantly improve the recommendation preference, which indicate the importance of knowledge transfer across domains. And we can also adjust that the inter-domain preference contrasting learning significantly improve the model performance. It shows the importance of catching the complementary information of user preference in the target and source domain. So I hope this answers your questions.
Thank you. Any other question? So I have another question. So in your research question 4, you asked what is the influence of the hyperparameters, right?
Yeah.
Right? Research question 4.
Question 4. Yes.
Yeah. So is this a research question or just an optimization? So the results that you got for this research question, are they generalizable to other domains, other data sets, or do they hold just for your case?
Yes, we have conducted experiment to answer this question. So in this subsection, we explore the influence of the 3 parameters on the model preference. We study the weight of the target item representation contrasting learning task and the weight of the source domain item representation contrastive learning task, and the weight of the user preference contrastive learning task. Yes, so we vary the value of the partner in the range and report the results in the features.
But would these results, these ratios of the hyperparameters hold for other data sets as well, or just for this data set?
Just for these days.
Okay, so it's a hyperparameter optimization.
Yes.
Okay, thank you. Any other questions? Okay, then I would ask you for another round of applause for our speaker.